Okay, so now we are live.
Yes.
I think there are still a couple of people to wait. Anyway, I'm going to say a couple of things, general things. So first, welcome back to anyone. It's nice to see you again. I'm in France. I'm back in France, but I won't come to the office because I'm scared. We are scared, so we'll stay at home. But I hope I'll see you soon. And so, yeah, I'm happy that that's the first meeting for this semester, and we already have a plan for the next for the meetings. I already discussed with Aurelien this morning about the possibility of having a second meeting, so there is no need to rush and to speak too fast about topics today. We can leave a part of the topics to another meeting, which could be next week or another day, depending on Aurelien. And then I thought about actually asking Craig Callender if he wants to join, because Aurelien suggested to read a paper of him, and I know also some other people studied this paper quite well on probability in Bohmian mechanics. Maybe we can try to have him, and it would be nice to like continue the discussion with him. He's a very nice person, besides being a very great philosopher. The problem is that he's in Los Angeles, which means that we would have to meet at, I think, 5 p.m. would be possible, 5 to 7, because for him it would be 8 in the morning, still doable. He's a morning guy, but usually goes surfing in the morning, so I don't want to spoil his surfing. And then if Laurie agrees, Laurie and I are working on a paper on metaphysics of quantum switch. And I thought it would be nice to present our paper, and then maybe have also, or maybe first have Cyril introducing the topic, and then Laurie and I can present our paper, or the other way around. But roughly, we will have 2 or 3 meetings on the quantum switch. And then we'll get to November, when probably we will have Vincent giving a talk on structuralism, and we will see how many meetings do on this topic. So this is more or less the plan. Again, if you have something to present, let me know as soon as possible so I can fit it in the program. That was my very short presentation. I'm really tired, and so I speak slowly and stuff, but I'm okay. So yeah, I think we can start. Again, I'm going to change host. Aurelien, as I explained to you this morning, this means that if someone comes late, I have to ask you to accept them. I don't think there's, maybe there's Alexia and the other Pierre, but yeah, we will figure out. So thank you, Aurelien, for coming. So you all know Aurelien because he's based in Grenoble. I met him this morning. He's really nice. So thank you for this. And yeah, so I have to wait 1 sec. Okay. So now you should be host, and you can share the slide again. Everyone can interrupt. If you have clarificatory question on the slide, keep your objections and other stuff till the end, please. And write, if you need to ask something, please write on the chat so I can see and interrupt Aurelien. Okay. And that's all. Thank you, Aurelien.
So let's do it. So I have to share the screen. It works like that. And how is it? I have to remove this because it's blocking. Okay. Yes. Presentation. Okay. I think I've all. Okay. So great. So thank you, Christian. So it's perfect for me. I'm very pleased to have an occasion to speak, especially in this period when you cannot discuss too much avec, in a real life, let's say. So this is very great. And so my topic is the Double-slit pilotway theory. And I will try to focus on one interesting topic in the Bohmian community, which is the justification of the Bohm rules, the probability rules in quantum mechanics, which is not so often discussed, and because it is very often said that the Broglie-Bohm theory is empirically equivalent to standard quantum mechanics, but this is not so complete. It's not completely true actually, because Bohmian mechanics is a deterministic approach, whereas standard quantum mechanics is essentially stochastics. So you can imagine that there is a difficulty to justify Bohm rules in the Broglie-Bohm theory. So I will try to give you a brief introduction to that topic. So as I say this morning with Christian, I think it's better that I focus on some general issue today. So I will discuss the main I would say proponents, the main let's say school of thought concerning this probability interpretation in Bohmian mechanics, and my own personal idea. We'll discuss it maybe next time. It will be better like that. I will not have to hurry up and to put too much things. It's already quite technical, so I will try to be clear and to let time for discussion. So the first thing I would like to say, to remind, oh, I have to go, yeah, that's fine. So the first thing that I have to say is that, as you know all, the standard quantum mechanics is probabilistic in its nature, by its nature. So it means that if you send, for example, a single photon to beam splitters, a device which would separate beams, you will have the possibility to predict the amplitude of the beam using Maxwell's equations, at least for working with single photon. You simply use the standard classical Maxwell equations, and you can compute amplitude for the different canals. And the general rule of standard quantum mechanics is to square this amplitude and to say you have a probability for the different outcomes. And from the point of view of Max Born, this is a postulate, so you have to accept that the probability is a genuine randomness. You cannot justify with a deeper hidden mechanic, the law of nature. So this is the statement that the wave function is a catalog of knowledge for all the outcomes that you have. And you can imagine that not everyone agrees with that. Specifically, Albert Einstein was a strong opponent to this way of thinking. He was debating with Max Born and also with Niels Bohr. And for him, for Albert Einstein, the interpretation of statistics is connected to classical randomness. So for him, it was clear that there is something that we ignore at the more fundamental level, some hidden variable. And this represents for him what he called the statistical interpretation, which is different from what Max Born called the statistical interpretation. So the statistical interpretation of Einstein was also advocated by some Russian physicist, Blokintsev, in the 50s, and Let's Valentine, for example, an American physicist, wrote a very nice paper that reference is written here. And for them, so everything is connected to classical ignorance. So if you say that it's classical ignorance, then you have this issue which is coming. You are making a parallel between quantum mechanics and classical statistical mechanics. And then it means that all the big shots of standard classical statistical mechanics, like Ludwig Boltzmann, Willard Gibbs, Claude Shannon, Henri Poincaré, and many others, should have to play a role in the discussion. So all the argumentation that you are using in Bohmian mechanics are a mixture of this kind of things, so like determinism plus initial conditions, so the ignorance of the initial conditions, and the role of entropy as well. We have to be really introduced in the discussion. And you can imagine that the usual idea that we found in that you find in a statistical mechanic, the classical statistical mechanic will appear. So, for example, the hypothesis of molecular chaos, which was introduced by Boltzmann, for justifying the presence of probability in gas, like is connected to the complexity and the possibility to control the motion of the particles. And you have also the deterministic chaos hypothesis, which was discovered by Henri Poincaré, which is connected to the high sensitivity in the motion of particles. For example, if you have two particles that are very close to one another, and the motion will be very, very strongly dependent on where they are coming from, in different BRs and different gravity, you will have different behavior. And this is probably playing a big role in Bohmian mechanics as well. So the other big issue in this problem is the notion of probability.
Sorry, Aurelien, to interrupt just one tiny second. Can you go to participant and accept?
Yes, I can. I have to do, probably I have to participant, new participant. Who is coming? Admit, yes, two people. I have admit two. I admit. I think it's two people. One in yes, I think it's okay.
Who is late?
That would be me, sorry.
So I think it's fine, no? Yeah.
Yeah. Thank you.
Oh, you're welcome. Yeah, so so where I was, yes, I was speaking about the role of probability in classical mechanics, and now I have to say only a few words about another issue about the problem of the probability. Is the probability, as you know, have two phases. One side is called objective probability, and the second side is called subjective. And there's a lot of debate concerning the nature and definition of probability in the mathematician community and also in the physics community. For many people, the probability is essentially a frequency of occurrence, so a ratio between the number of time and outcome alpha occurs divided by the total number of n that you reproduce the experiment. So this is valid in the limit of large n. And so this is the frequentist Q point of view. And there's also a Bayesian point of view, which is more difficult to define clearly because the probability is called credence and is going back to the work of Bayes and Laplace. And it's a number that actually is assigned to the event. And sometimes people are telling that it's a subjective probability. And this event is assigned to individual event, whereas the frequency point of view is connected to the sequence, so to an ensemble or collective. This is a very complicated subject, and philosophers are probably better oriented than me on this topic. So only I will have probably to go back to this issue when I will discuss the law of large number later. But this is the second big, you see, topic in the problem. So you have the classical mechanic, you have you have Boltzmann, you have Maxwell, you have Gibbs, and then you have also all this issue concerning the signification, the meaning of probability. Now the thing is, here I'm going to discuss a specific interpretation called the pilot wave interpretation. So you know that this pilot wave interpretation is called Bohmian mechanic, because it has been rediscovered by Double-Bohm in 1952. Actually, the theory was introduced by Louis de Broglie in 1925-1926, and he presented the version of it at the 5th Solvay Congress. And due to the complexity of the subject, and because de Broglie could not fight too much with people like Bohr and Heisenberg, he abandoned his theory quickly after the conference, even though he was supported a little bit by Albert Einstein and Léon Brillouin. And then he abandoned the theory during 25 years. And the theory was rediscovered by Double-Bohm in 51 and 52. But actually, it's even more funny because not too many people know that another American physicist called Kennard rediscovered independently of de Broglie in 1928 the same interpretation. So only 1 year after de Broglie abandoned it. And so he also abandoned the theory after that. And Nathan Rosen, the famous collaborator of Albert Einstein in the EPA paper, also discovered the theory in 1945. And again, he abandoned it completely. So the pressure of the social environment was clear. Is a clear reason for justifying this promises abandon, this difficulty to work with this topic. But there are also probably some mathematical and physical difficulty, because when you are working alone on this topic and you don't find some mathematical support, it's difficult to work on it. So anyway, this is a sociological aspect, which is interesting for me. But the point which is interesting is that the Broglie-Bohm theory can be understood easily if you go back to the picture of Broglie. So Broglie thought about the particle as a kind of singularity, which is riding atop of a wave. This wave is a base wave, a guiding wave, and the analogy is the surfer on the wave on the sea. So the surfer will be guided by the wave and be following one specific path. And depending if, for example, there's an obstacle like this island here drawn on this picture, you will follow one path, but the wave will go both ways, and they could interfere and influence the motion of the particle. Now, this view is, of course, completely different from the perspective of Heisenberg and Bohr, where the wave is split, and somehow the particle is losing its identity, its nature as an object in between. So this is the intuitive way of thinking about the problem. So one of the motivations for the Broglie-Bohm theory is connected to the wave-particle duality, so the possibility to interpret the wave-particle duality. As I say, David Bohm rediscovered the theory in 1951, but he abandoned also the theory after 10 years. And he was actually going back to the theory at the end of the 70s, when one of his collaborators showed some graphic made by some students. They were interested in computer studies, and they were computing the trajectory made by Bohmian particles in the double-slit experiment. So this is one kind of this simulation that I show you. It is not exactly the same that they did in the 79, but it doesn't matter. So you can recognize here the double-slit experiment. I use actually Gaussian beams instead of slits, doesn't matter. So we have 2 points A and B, 2 sources A and B. The Gaussian beams are propagating and spreading, and then you have interference pattern in the far field. And you can compute the path using the Bohmian mechanic. And the rule is quite simple to understand. For the single electron, you take the wave function C, you separate it into a modulus and into a phase. And here we put the Planck constant equal to 1 to simplify a bit the notation, but h bar equal 1. But the rule is the following: you take the gradient of the phase and you divide by the mass, and then you have the velocity of the particle. And then with this velocity, you can compute the trajectory analytically or numerically. And that are the trajectory that you obtain in the double-slit experiment. And you see that they are complicated sometimes, but they are going to somehow to be more numerous, more present in a zone of the of the maxima of the interference fringes. And I also will show you this sentence, which was written by John Bell in 1982. He said that in 1952, I saw the impossible dawn. Okay, it's important to say that John Bell was a strong advocate of this theory. And it was also one of his motivations for discovering the famous Bell theorem on non-locality. And there is one issue concerning the theory which is interesting, which is concerning the contextuality, in the sense that, and the wave-particle duality more precisely, in the sense that now if you are closing one slit, you see that the trajectory are very much different. So you're closing the slit B, and now you have simply a single slit pattern in the far field, and you have one big blob, like one Gaussian blob like that. And the trajectory are completely different from the double slit. And what it means is that the particle paths are strongly influenced by the wave and by the environment in which they are propagating. And you cannot say, like Heisenberg and Bohr, that it's not possible to reproduce the double slit experiment using, let's say, classical path interpretation, because they were thinking about classical path in the sense of classical mechanics. But you see that it's more sophisticated and more complicated in the case of Bohmian mechanics. So this is the motivation for the Bohmian mechanic. And now, in order to be more precise, I have to give you some mathematical idea about it, because otherwise we will not be understand the probability problem, the probability conundrum. So here I show you on the simplest model that you can think about. So it's you start with the Schrödinger equation for a non-relativistic electron with an electron in a external potential V, and then, as I said before, you write the wave function as a complex number, and you have a separation between modulus and phase. And if you introduce this in the Schrödinger equation, you can separate the imaginary part and the real part. And the real part of the equation is here. It's a so-called Hamilton-Jacobi or Euler equation, which is playing a big role in standard classical mechanics. You recognize probably here the formula from classical mechanics. Here, in the left, you have the energy, which is the time derivative of the action, of the phase, which is playing the role of the Hamilton-Jacobi action. And here you have the separation of this energy into different terms. So you have the kinetic energy, which is the momentum squared divided by 2 times the mass. So you recognize this formula here, which is classical, because the momentum, which is the gradient of S, divided by the mass gives you the velocity, which is the standard definition. And you have also other terms in the energy, like the potential, the external potential on which the particle is moving. And you have also an external term, an additional term, which is called the quantum potential, which is specifically quantum in the sense that if you go to classical regime, it's vanishing asymptotically. So you recover classical mechanics. But this term is completely fundamental because it's giving you specifying you the dynamics of Bohmian mechanics. So with this, you can compute the path of the Bohmian particle, because if you know the gradient, you can compute the trajectory. You can integrate this equation. It's called a first-order differential equation, and you can obtain the deterministic path of the particle. And also, if you want to connect the theory to the Newtonian formalism, the most classical Newtonian formalism, it's simple because you can take the Hamilton-Jacobi equation, you can derive it a bit more, and you take the following law, which is the mass times the acceleration, equal a force, and the force is divided a classical force, which is the gradient of the potential, and the gradient of quantum potential, so give you a quantum force. So you see that you will be able with this approach to have a picture which is not so different from the classical picture, where you have an additional quantum force. So this is the dynamic. And now the second thing is that you have imaginary part, and you can derive a second equation which is called the local current conservation. And you know this equation because you have it in all textbooks in quantum mechanics. This is the divergence of a current, which is the current of probability, which is equal to minus the time derivative of a density, which is equal to psi squared. So the Bohm rule somehow. So you see that this current is also written in normal textbook and is equal to the density times the velocity. So you have really a flow of particles, a flow of a fluid, let's say. And sometimes in modern textbook about Bohmian mechanics, in modern articles, people try to simply summarize the Bohmian mechanics with this current formalism, this current versus density formalism. So they say that if you want to compute the velocity, you simply have to take the current, you divide it by the density, and you get the formula. So you don't need to even to go to the Hamilton-Jacobi and all these kind of things that I showed you before. Simply take the current divided by the current. By the density, excuse me. But of course, for me, it's a bit too much because you lose, you remove all the nice physical ingredients which are justifying the dynamic. But still, you can live with that. Okay, so it's not a problem. Now, if you want to go to the topic of probability, you need to go to the standard definition of a probability in statistical mechanics. So you need to introduce an ensemble or collective, that is called by mathematicians. So you suppose that you have a fluid of particles, which are representing a small cloud here, delta, where you have many particles inside a small region of space, and they are identical copy of the same system. So, and they are following the trajectory. And so they are like that, define a flow of probability. this is a rough way of defining it. So you have like that a way to justify the conservation of the probability flow, meaning that if you want, you can say that you have if you compute the number of particles in the volume delta X, and you see how it's going with time, you see that this number is a constant of motion, so because you have conservation of probability. And if you know a bit of statistical mechanics, you know that there is a famous theorem in statistical mechanics called Liouville theorem. And this is very similar to what we have in quantum mechanics. And because it's interesting to see this analogy, I think it's good to go back a bit to classical mechanics, because you are going like that to see what is the definition. So in standard classical mechanics, normally people are using the Hamilton formalism. So you are working in Hamiltonian space, you have two variables Q and P, so conjugate variable, and you have the Hamilton function. And you can have this Hamiltonian space with different dimensions. And you can compute the flow, the trajectory like that, as is shown in this illustration. And what is nice is that you can introduce a probability measure in phase space, which is called the volume, simply because it has the property of a volume, so dq dp, and it is fundamental to introduce this quantity as an invariant, so because it was claimed. It was claimed by Henri Poincaré. If you don't have an invariant, it's difficult to speak about probability. And indeed, it is an invariant in the sense that if you define a probability that you can say as a density times volume, you can demonstrate with the property of Hamilton equations that the density is a constant of motion over the path, along the path, and also the volume, the small volume of is preserved in time. So if you take, for example, this picture here, you see that the small volume V0 is transformed into a new one, which is very complicated sometimes, but the volume is is conserved, has the same value. Here, this is the same. It is very similar to Bohmian mechanics, and I'm going to insist a bit on that because it's very interesting. If you take the Schrödinger equation, as I say, you can define the conservation current. So you have the divergence of a current, and you have the divergence of and you have the time derivative of a density. This is from Schrödinger equation. You don't need to use Bohmian mechanics for that. But now, if you want to go to Bohmian mechanics, you want to introduce a density of probability. So you will have a conservation law with a divergence of a current of probability and a density of probability rho. And in general, you don't have to have rho and psi square identical. You can introduce a coefficient f of proportionality, and f will be some property of the system, and actually it will be the genuine density of probability in a configuration space. Because if you want, you can introduce a specific volume in a configuration space, which is psi square times dx, so the volume in the phase space, in the configuration space, and this is preserved in time. So you can demonstrate with the Schrödinger equation and with the property of Bohmian mechanics, and if you take a small volume delta gamma, it's preserving time along the trajectory, and the f function, the density that I call the density of probability f, is also a constant of motion. So you have really an analogy with the Liouville theorem and with the notation that we use in normal statistical mechanics.
Sorry, Aurelien, there is a clarificatory question.
Yes.
Yeah, so I just did not really understand why do we need to preserve the volume in the phase space along the evolution? I didn't get that. What you said on the previous slide.
Yeah, okay. The reason is that if you want, actually, normally when you think about intuition probability, you don't need to do that, okay? But people, for example, they are defining probability in a quantity which is by definition always constant. For example, if you define if you use the Maxwell formula for the probability for the velocity probability for the distribution, you use an assumption that dv is a kind of property of which is defining your space of evolution, and you don't want that is evolving. So you use it.
That's why, yeah. I'm not sure to understand why, because it's a matter of mathematical modeling. It's not really a matter of physics. Would you agree?
Yes, it's a matter of modeling, but it plays a lot of. It has a big. You enter really in the debate of the meaning of this probability and of this probability measure. The community is accepting this issue somehow because it's working fine. And indeed, if you introduce this this delta gamma volume, you observe that it's a constant of motion. So at the beginning, you say, okay, it's simply a fact. You don't have to consider it as a need. But the Poincaré emphasizes that it is fundamental to have this kind of quantity, because if you have this kind of quantity, you can speak about something which is stable in time, you know. For example, Albert Einstein was present at the first Solvay Congress and debating with Henri Poincaré about the status of probability, and one of the reasons of the debate was about this notion of volume, space.
Okay.
That issue, I agree.
So just to make an analogy so would you agree that like dq dp is the kind in a way the unit of the probability, and we would like the unit to be constant in an analog way, in a way? If the unit evolves in time, it's not necessarily a problem, but it's weird.
Yes, I think it's a good analogy. Yeah.
Okay. And just another question about your next slide. So just to understand, so the modulus square of psi in this framework, you multiply it by the function f. So in the end, does the modulus square give you the density probability of the Bohmian particle? This I didn't totally get.
I agree. I was a little bit fast. The density rho is the density of probability in a volume. So if you take a rho times the volume, the physical volume in the configuration space, the x will obtain a probability. But if you introduce a new definition and you introduce delta gamma as your measure of the physical configuration space, then the function f is the actual density of probability. And at the end, the total probability is independent of the way you measure it. Okay, it could be gamma, it could be rho times dx or f times the gamma. But this is the same. It's the same.
Okay, and what is the motivation to introduce this extra f? Why don't we work with the?
Very convenient for the rest of the reasoning, because then when you're going, I will show you in the next slide. You have a lot of similarity with the formalism of standard classical mechanics and standard statistical mechanics. So all the reasoning that are done in a statistical mechanic, as I will show you, can be somehow used in a Bohmian mechanic. Without it's more complicated to see the point.
Okay, thanks.
That's the reason. And also, I want just in fact, this is making the transition. The reason why it is very convenient is that now you see in the Bohm rule, in this notation is meaning that f equals 1. But f equals 1, it has a statistical meaning in a nation of in a statistical mechanic. It's called the microcanonical ensemble. This is the equiprobability ensemble. So you see that it's very convenient to use this measure, delta gamma, because with this measure, the Bohm rule is simply the fact that all the points in your gamma space are equivalent. You see. So when you say that, the question is why f should be equal to 1. That is the question that you have in Bohmian mechanic, and you don't have in standard quantum mechanic. Because in Bohmian mechanic, in standard quantum mechanic, you assume from the start that you have the Bohm rule, so you assume that f equals 1. But Pauli and another American physicist wrote that that is very mysterious, and you have to find a justification for Bohm rule in Bohmian mechanic. And so people try to find this justification. And one of the older justification is going back to De Broglie. So De Broglie thought about that problem already in 26, much before the objection of Pauli. And for him, the reason why f equals 1 is a good intuitive thing is that he was considering the following reasoning. Imagine that you have a plane wave. So a plane wave is homogeneous and isotropical. So all the points in the plane wave are equivalent. So he was applying kind of principle of indifference in the sense of Laplace. So all the points are equivalent. So you have intuitively the will to put f equals 1 as a natural probability. So he was thinking that intuitively this should be the case. He was not able to go further. But then he said, no, imagine that you have not a plane wave. Imagine that you have a plane wave going to interact with an obstacle, like an atom on a diffracting center. Then this plane wave will be scattered, and it will have many waves. And as from what I said before, the f function is a constant of motion, so it's preserved during the evolution. And he said, okay, if initially f equal 1, after a while it will still be equal 1, even after the interaction, and even after a while, so when the wave is very complicated, you will have the Born rule, which is holding. You see? So if you assume that f equal 1 in the past, it has to be true in the future. And so he was thinking in that way. It was a kind of intuition for him. And what is interesting in with this picture, that it is connected somehow to more modern language of Bayesianism. More precisely, if you go back to the point of view of Jens, who was working on statistical mechanics, you go back to the point of view of Gibbs, Jens, and Shannon, and you try to maximize your ignorance. So what is the point of view of Jens? Even though Jens was not speaking about Bohmian mechanics, this is my interpretation of it, okay? So Jens say, okay, imagine that you have an entropy function. So the entropy, instead of using the entropy, I use the H function, which is minus the entropy, which is very common in statistical mechanics. And I define the H function as f log f, integrated over the gamma space. As you see, I remind here what is the gamma measure, so the gamma space measure. And then, in order to maximize your ignorance, you say, okay, I will compute the variation of H functions. I will find the experiment with a constraint, which is the probability has to be preserved. And when I do that, I obtain without any possibility, or the possibility, then the f should be function should be a constant. And since it is by normalization, it should be equal 1. So if you admit this idea of maximizing ignorance with the only constraint and probability should be a constant, then you get equiprobability in the gamma space. You get this microcanonical ensemble, and then you get the Born rule. So you see, this is very similar to what we do in statistical mechanics. Sometimes, if you want to, for example, to apply the same kind of maximizing the ignorance, it's called the maximizing of entropy, maximum entropy principle by Jens. You can add some other constraint. For example, you can add the energy constraint and things like that, and then you get, for example, the Boltzmann-Gibbs formula for the probability of the exponential, etc., etc. Then we get the canonical ensemble, but here we are only interested in the microcanonical ensemble. So you see, it's natural to think about it, but it's mathematical, of course. It's a bit interesting if you want to justify it, but there's some mystery, some magic, I think, behind it. But I like it anyway because it's one of the languages used by the community of people working in statistical mechanics. Okay. The other way to see the problem, which is much
there is a question about the...
Yes.
Yeah, sorry, another question, because what I didn't get is that, so I understand what you do here. You add a function f to this measure you have, and you see that f equal to 1 is the one that maximizes ignorance, and okay, you have Born rule, but the thing is that you in your measure, you assume that the modulus square of psi enter in your measure, so...
Yes, you're right. You cannot...
Yeah.
But the thing which is nice is that oh, sorry, sorry for you. So the psi square function is very often associated with the probability, but here, if I introduce it as a measure, which is simply, I have always the right to do it, simply
yes.
Then I can simplify my reasoning, because the delta gamma volume is a constant of motion, is preserved with time. So it has the nice property to be a constant along the path. It's only for this I'm going to do it. But of course, if you want, you can simply use normal dx volume, and you can define the density probability rho, and then you will have some kind of relative entropy, where we will have here rho divided by c square, and you will have to make the reasoning with using this way of thinking. But you see, it's only a way of thinking about the f function as a relative probability. Okay.
So in terms, yeah, physically, I'm not sure then to have got the the point of doing this? Like, what, which insight does that give to put it in the measure and do this stuff? I don't get it.
But the thing is that if you don't do it, as I say, you can use row function. Then you will have to introduce a nice objective way to define the entropy. And then you will see that if you use dx as a volume, and if you put rho instead of f here, this function will not have a nice property and the gamma volume will not be preserved. Because the dx volume will be changed in shape and the volume will not be conserved, but the gamma measure is preserved. So you can, when you compute the derivative, it's much simpler to use this. It's the reason why I'm using this as well.
Because with this d gamma, with this measure of volume, using the equation of motion, we see that it's preserved along the path. Is that what you mean? Okay. Okay. So then it's more convenient with the discussion we had before. The volume is conserved, and then it's okay.
I see that as a nice notation that I think should be more universal for Bohmian mechanics. Maybe I think it's a good notation even would be beyond the context of Bohmian mechanics, because it helps a bit to understand what is the status of Born rules. But the other way to see the Born rules, which is much more discussed in the literature, and maybe you saw this in some paper, is the Boltzmann way of thinking about probability. So it's called typicality in the language of the Boltzmann mechanics. So the way of thinking about this is the following. You imagine a quantum experiment where you send, for example, an electron to a Stern-Gerlach apparatus. So you have many outcomes, many separate beams, and then you make the experiment once and you obtain one result. You do again the same experiment with the same experimental condition. So it could be the same apparatus or another apparatus in other place of the universe or in other time, doesn't matter. You do again the experiment with the same kind of preparation, and you obtain maybe another result, maybe the same, doesn't matter. Then you do it again and again and again. You will produce n time at the end of the experiment. So you have repetition. And now you have this famous law of large number, which is telling you that if you define n alpha, the number of times that you have the outcome alpha, and n the total number of repetition, then the law of large number is telling you that frequency tends to weight with high weight. So here, paraphrasing the sentence by David Wallace, a famous physicist working in the many-word interpretation, but I found this summary of the law of large number very good, because what it means actually, this sentence is the following: the frequency is the ratio n alpha over n, so is what we use in statistics. The weight here for those people who use this argumentation is the chi-square wave function, so the gamma wave, the gamma amplitude, as I said before, in a certain sense, because here it's a discrete space, so I use discrete outcomes. So I have to integrate the gamma cells over the width of the exit beam, and then I obtain this is identical to the square of the amplitude associated with the different modes. Okay, you can easily understand that. And if you do that, you say that the law of large number predict that with high weight, so you will have identity between these two quantities, the frequency and the weight. So the high weight means that the probability, which is defined by the measure in the gamma space, that the p alpha equal n alpha over n is approaching 1, and in a typical sense, we say. And if you say that, it means that all the region of space where the law of large, where the Born rules holds, so the p alpha equal n alpha over n is the overwhelming majority of the gamma space. So you say that it's typical, and we say that you have the law of large number. So in the 90s, in the early 90s, three people, three collaborators, Zanghi, Du, and Goldstein, represented in this photo, wrote a series of papers about that. Here I give you the reference for the shorter of them. It's in a physics letter, it's a few pages only, but they are a very long paper about this topic. And they say, okay, this is the final proof, somehow then your Born rules should hold. And it has sometimes been said that it's the official way of thinking of Bohmian people. So, but I don't completely agree with that, because there are people which are thinking that this is a bit circular. And one famous guy who said that is circular is Anthony Valentini. Anthony Valentini, this is this guy here, who wrote also in the 90s another approach that we discussed a bit after, and we claim that the reasoning of Gaussian and Zengi is circular because your notion of weight is somewhat arbitrary. And this is going back to the question that you asked before. So indeed, why I should use a weight gamma? Maybe I should I could introduce this f function and to have another definition of probability, which would be p prime instead of p. And then if I do that, all my reasoning will be modified. I will have to apply the law of large number with this new measure p prime, and I will be able to define the law of large number. This can be demonstrated very rigorously. But if you do that, you will obtain a different law. You will obtain, of course, a law which is not the law of Max Born. You will obtain a law where you have this f function, which is introduced in prefactor. And say Valentini, there is lots of circularity in the reasoning. And somehow this is normal because you have to think that the reasoning about typicality is a way of defining a probability, okay? For me, it's a way of thinking a frequency should equal the Bayesian probability using the law of large number, but it's only showing you that the two probability, Bayesian and frequency, are not independent, as people often claim. They are identical. They are the same thing. And if you think about that seriously, you realize that you cannot use the law of large number as a way for proving your law. It's only a definition of probability. You use what is called a Gibbs collective or Gibbs ensemble, because when you go to the limit of n infinite, you define the probability space using this Gibbs collective and Gibbs ensemble. Whereas if you take n finite, you don't have this possibility to define rigorously the probability. So you see, this is the mathematical definition of probability, which is introduced by Bayesian, is having only a physical meaning through the limit of the repetition of events. So yeah, and yes, it's really the core for me of the philosophy of probability. And Valentini is fighting, I think, against Gaussian and Zengi about the circularity of their reasoning. And this, I think, is very difficult debate. And probably we could discuss longly about that. But and maybe people would disagree with, and if you watch in the literature, you will see different point of view about that. So I give you only mine view here, is the reason why I'm telling you that I subscribe to the view of Valentini, but many people will say that's not true, okay? So you have to think about it yourself, probably. Yeah, and the point of view of Valentini is that, okay, you have the vocabulary used in a Bohmian community is the following. You have the view of Gaussian and Zengi, which is called the equivariant probability, because they say that the density probability is equal to Born rules, because the chi-square wave function is the most natural way of defining the probability. You can say that it's the only way of defining the density probability, which is depending only of the wave function itself, of the square of the wave function. You can derive it mathematically, and then they say, okay, it's normal to say that you have to use these Born rules. So they try to make a mathematical justification of it, but it's not physical. Okay, there's a lot of circularity again in the reasoning. And Valentini said, no, you have no right to say that. Maybe you have to find a better justification for Born rules, because the most general rules is non-equivariant and non-equilibrium. Okay, so yes, this notation, I don't know if you understand, is a chi-square is the density probability of Born rules, and here is the empirical notation for the distribution. So if you are going, is the equivalent to the notation n alpha over n somehow. Okay, but this is the notation with Dirac function, but it's okay, it's like that. And so the view of Valentini and Gaussian and Zengi is interesting. And actually, Valentini has his own perspective on it. He says the following: maybe the Boltzmann perspective is not the best. He preferred the perspective of Gibbs and also the perspective of Tolman and Ehrenfest. Tolman was also a specialist in astrophysics and was working, I think, with Einstein. And Ehrenfest is a known physicist, of course. And he wrote also, he was, I think, a student of Boltzmann, and so he knows a lot about statistical mechanics. And so the way of thinking of Valentini is the following. So you take your gamma space, for example, an electron, and you separate it in many cells. So you introduce a coarse-graining. The coarse-graining means that you separate in small finite cells your space. So, and you introduce f average F space on the cell. Okay, instead of working with the fine graining, you work with the coarse graining. And if you work with the coarse graining, you have two entropy functions, two H functions. One is the fine graining, which is F log the F, and the second one is coarse graining, which is H bar, which is F bar log F bar. Okay, and then you can demonstrate mathematically that if you compare these two H functions, you have an inequality which is obtained very quickly, telling you that H bar is always smaller than H. Okay, this is you can demonstrate it. It's discussed rigorously in many textbooks in statistical mechanics, but it's also present in an article by Valentini here. And with this, as a starting point, Valentini say, okay, now we have conservation of the H function. This is the equivalent of the conservation of the entropy in Gibbs space. So in the phase, the entropy is a constant of motion. And here the H function, so the H at the fine grained level is a constant of motion. And so you deduce that the H function at time t equal the H function at time 0. But now he's introducing a postulate, which is the postulate that at the initial time, your fine graining is equal to the coarse graining. So you say that the fine grained distribution is equal to the coarse grained distribution. This is an assumption that is done by all these people. And if you do that, then you have immediately the H bar function is decaying with time somehow. But it's decaying in a specific way. It's simply telling you that the H function on time t is smaller than the H function on time 0. Actually, very often people say they won't like to have this derivative of H bar, which is smaller than which is negative. It means that the entropy is growing because the entropy is the negative of this. But this is not true. Actually, you cannot go from that to that. In particular, if you take 2 times T1 and T2, you don't have the right to compare T1 and T2. You can only compare T1 and T0 and T2 and T0, but no possibility between T1 and T2. Okay. And anyway, if you assume that there's a possibility to go from this to this, as many people do, then you have indeed a kind of irreversible dynamic, which is breaking the time symmetry, which is a bit mysterious because you cannot break time. You cannot break time symmetry in a time symmetric dynamic like that. So it's really connected to the initial condition. And Valentini tried to show that the F bar function is going asymptotically to 1. So he's approaching the microcanonical ensemble. And his reasoning is connected to the ink drop mixing analogy that is used by Gibbs in his first book in statistical mechanics at the beginning of the 20th century. So I remind you briefly this ink drop mixing analogy because it's very interesting. So imagine a tank of water, you put a drop of ink inside, so small ink drop. So the drop will change its shape, the volume will be preserved like in configuration space. So it's again emphasizing the role of the gamma space which has to be preserved. The volume will be more and more complicated and very, very filamentary. It will occupy all the space. But if you take the coarse-grained definition, so you will see that the density of ink is more or less homogeneous and constant over the tank after a while. So it, of course, it depends on the time, it depends on the cells, but says Valentini, this should be the way of thinking about the tendency to find a quantum equilibrium. And in order to go to that point, Valentini say, okay, my analytical calculation are maybe too rough and they can be criticized. Actually, many people criticize this kind of calculation already much before Valentini because it's a classical reasoning. But he said, okay, I will make numerical computations. So he did many numerical computations with collaborators over the years. So here I'm showing you one of them in a paper of 2012. And so you can read this simulation in the following way. This is a two-dimensional system, so only 2 degrees of freedom. And you compute the chi-square function density in the square, that you can see here. So I don't remember what was the Hamiltonian. I think it was the sum of oscillator. And the system is anyway periodic in time. So you can see that this is t equals 0, t equals 2 pi, and t equals 4 pi. So the pattern here is at time initial t is 0. This is t equal 2 pi, and this equal 4 pi. And you see that the pattern is the same. So periodically reproducing the same feature. And now say, okay, this is the Bohm law, the Bohm rule, which is assumed from the start. And now imagine that you have a Bohm law, so you assume that rho is not equal to chi squared, so you have a f function which is different of 1. So he's using in this simulation this kind of pattern, which is a kind of Gaussian, I think. And you see that now he can use the Bohmian mechanic to compute the evolution. And he said that with time, so the derivative of the h function is decaying. The simulation is showing that rigorously at the coarse-grained level. And it's approaching progressively the chi-square function. So I have to say that this is a specific simulation. It is a very simple model. And it has been criticized by many people for probably good reason, because it's not generic. It means that it's depending from the system that you're considering, and it's also depending of the chaos that you have in your system. So, for example, it has been demonstrated that if you have some, you have sometimes some limit cycle which are not favorizing this tendency to reach quantum equilibrium. So you have some domain where the quantum equilibrium is not obtained. And then say Valentini, okay, anyway, we have to find more simulation, more complicated demonstration, and he's trying to apply his theory to the Big Bang. So his research is going in that direction, and he's, for example, he's applying the approach to the cosmological. To the CMB, to the cosmological microwave background, to try to discover some relic, some defect in the Born law at the initial time of the universe, and to find that there is some maybe some signature of deviation at nowadays. So yeah, that's the way of thinking about Valentini. And I think now I will stop. Okay, I will stop. With the slide, because I have many other possible discussion, but then you have a lot of mathematics already. We discuss a lot of things, and I think it's good now to have something to discuss to see if we can find if you can disagree or not. Yes, I think I'm open for questions.
Thank you.
Somebody is still here? Yeah.
Okay, so if you have questions, let me know either now or on the chat.
Yeah, I have another question related to the slides.
Even, I mean, I think now we're taking sort of either a break or we start the discussion. So even if you have more general point, it's not just clarificatory. You can go, Marco, of course.
Yeah, sorry. So it's related to your last slide. So just to summarize the thing. So the point, as far as I understood, is that so you add this function f to the psi squared dx, and the point of that is to show that after some equilibrium, in a way, necessarily this function f goes to 1. So if you wait long enough, like the Born rules is the equilibrium. Is it that?
Equation, yeah, kinetic equations in Boltzmann equations. Okay.
Okay. Yeah, and so I'm not sure. So of course there are hypotheses behind this. So what were the general hypotheses? It was the entropy at 0. Can you remind?
Yeah. Okay. No, this is yeah. So the thing is, the hypothesis is mainly the coarse-graining, and this is the hypothesis. I cannot see at the same time the discussion. Yeah, I put the photo here. The camera. Yeah. So yeah, the main hypothesis is that it's defining some kind of coarse-graining at the initial time with the f function, and with this, is going to use Bohmian mechanics to see how it's evolving in time. And analytically, he was trying to demonstrate that the h function is decaying, but it's not possible using this kind of theorem to show it rigorously. So it's only a kind of crude tendency, a kind of guide for the reasoning. But if you want to demonstrate it, you have to go to a more precise example. And so he was using these simulations. But there are other groups which are making simulation of the same kind, which are telling that Valentini, you are not right. There are a lot of counterexamples. So you have to define a way of telling what is generic or not. And the problem is, like all the problem in the language of probability, you are going back somehow to the notion of typicality again. So what is typical, what is not typical, what is natural, what is not natural. And so you can imagine, and if we yet didn't understand the problem in a statistical mechanic after 1-2 centuries already in classical mechanics, it's not yet the case that we will understand in a Bohmian mechanic, because Bohmian mechanic is the same kind of theory than classical mechanic, even though the dynamics is different. So the problem that you have now in Bohmian mechanics are the same that we have from the start with the classical mechanic. From Clausius' time to nowadays, we don't understand yet the law of entropy, why the entropy is increasing. We would like to derive it, but there is a lot of work and a lot of, I think probably the law cannot be demonstrated generically. It means that there are a lot of exceptions, and we have to already say we are in a specific region of the configuration space, which is allowing the increase of entropy to be true, but there are counterexamples. So. Okay.
So I see roughly the thing, and then would you agree that in a way that's something that could be tested, this thing, because there is a dynamic behind, and if you go fast enough, you could see if the Born law is an equilibrium or.
Yeah, exactly. It could be tested, and the problem is that all these people are telling that it's very fast, and yeah, the system is too simple. And in fact, I would like maybe not today, but in the next talk to go to more specific dynamic when I will use the Boltzmann equation and really the interaction with the thermostat. But I simply focus on the way of thinking of Valentini, and which is intuitive, which is can be debated, because they are using only very simple model. You see some two-dimensional degree of freedom. Yeah. So the space is too simple maybe to get some generic to have a complete acceptance, okay, from the community. It's the reason why people are criticizing. So the two groups, the Duo-Gershon and Zengi on one side and the Valentini group on the other side, are fighting, especially because one will say one is tautological, and the second one will say this is useless because you are only using very simple particular example. So
okay, that's a debate. Thanks. That's a debate.
There's a follow-up on that, or I'm wrong? Okay. I'm wrong. Okay, so there's a question by Richard, a separate one, I think.
Hi, yes. So it's more of a question-y discussion point, get your opinion sort of thing. And I think it might be interesting to some of the others. Basically, it's in relation to the idea of background wave fields and what that means for the possibility of having a local hidden variables theory. So in particular, one thing I think is, well, one reason why I've ended up Bohmian, if I was to assign myself in any particular direction, is having seen the sort of, I forget the names now, but the water droplet oil drop experiment. That sort of, you look at it and you think there's some behavior going on here, which I don't think you should be able to see. And then you're told, okay, well, the reason it exists is because secretly when you're wobbling this tray and you leave it for a while, everything's bounced around, and secretly the background wave, if you like, has explored all of the territory. So everything knows where everything is. So implicitly you think, okay, well, I'm not surprised then. I get quantum-like behavior that seems to know where things are. Then you think again, and it makes you think, okay, well, that implies that the existence of a background wave field, obviously here under very, very specific conditions, but the existence of this background wave field has allowed me to see what looks like and is local hidden variables theory behavior.
Yeah, you're right.
And there is some work that shows that, well, it argues, I wouldn't say shows, argues that it doesn't need to be as stringent as that. The existence of a background field in itself is enough to potentially justify local hidden variables theories. And people turn to Bell's tests and say, the Bell experiments say this, Bell experiments say that, which are usually things that Bell never actually said, very much what people have derived from Bell. They'll turn and say you can't have a local hidden variables theory because of all these tests. But if you look at the specifics, they always say if particles and all the properties of the particles are created at the moment of the test, then things are invalid. But this does not apply at all to the existence of a local background field. And I wanted to know your thoughts on that, and if you think that's a particularly cross plus direction?
I think this is very interesting thing. Okay, yeah, we were discussing about Bohmian mechanics, which is non-local, which is a very specific way of solving the Bell theorem, because you know, all in the Bell theorem, you have another possibility is maybe to simply, instead of removing non-locality, instead of removing locality, you can also remove causality. And for example, you have time symmetry. You have some people which are thinking about making a retrocausal theory for explaining and justifying Bell's theorem. And also people trying to speak about what is called superdeterministic approach. Like John Bell was not a fan of that, but there are some people working on this topic. Personally, I am a fan of that, but this is a bit in conflict with Bohmian mechanics. I admit it, but okay. I'm working in a small group of people at the Néel Institute, where we are trying to find some mechanical analogy of quantum mechanics, and some of this mechanical analogy are going back to the picture of Louis de Broglie. And Louis de Broglie way of thinking is different from the Bohm point of view. You see at the beginning of my presentation, I'll show you briefly. Where is it? Oh, yeah. This picture of a soliton, a singularity wave riding atop of a wave, on a base wave. And the point of view of de Broglie is that this singularity wave is a bit similar to what you speak about the droplet experiment. And but the thing is completely local from the point of view of de Broglie. And de Broglie didn't accept the non-locality predicted by his own theory, never. And even in the 70s, he wrote a paper against the Bell theorem, which was completely wrong paper, but he published it. He was already more than 90 years old, so maybe, I think so, not so, something like that. Maybe he was quite old, okay? And he should have not published this paper, in my point of view, because he missed the point of Bell theorem. But I think the way of solving the issue is to introduce, as you say, some conspiracy. I think the conspiracy could be another way to discuss the interaction between particles, and then to eliminate non-locality. Okay, this is bringing us a bit far from the topic today, but not so far, because as you mentioned, Anthony Valentini is interested in watching some modification of the standard quantum mechanics rules in the laboratory. And for example, if you imagine that the Bohmian, the Born rules would not be valid in a double-slit experiment like the one here, then you could imagine very complicated things happening. If you are able to change the Born rules, so you can imagine that all your particles are located on one slit, even though you have a wave which is going through both slits. So if you do that, you are not Born rules anymore. You see, the particles are like this small cloud which are represented in blue here. They're only following this path, but the wave is really guided by both slits. And then you will have still this interference pattern. And if you, it means that, but only half of maybe of the interference pattern. It could be that only, you cannot see what I'm doing, but if you want, I can hide this zone here, and you will see only half of the interference pattern. And but this will be different from the single slit pattern. And this is because you will use the breaking of the Born rules. And this is another way to say the breaking of the Heisenberg uncertainty principle. So if you are able to find the breaking of the Heisenberg principle, of course, then you're becoming famous. And then I understand that Valentini is trying to find some argument, experimental argument for that. But it's difficult to say if he find anything. Okay, it's a program of research. It's a guess. And also for non-locality, as you mentioned, it will be possible to break. If you have break the non-signaling theorem, telling you that it's not possible to communicate faster than light. If you are able to break Born rules, so then you are able to transmit information faster than light. So this is also one of the claims made by Valentini. Yeah.
I suppose, can I respond or?
Yeah, sure.
I wasn't sure what the structure is. I suppose I'm kind of in my head mediating between the two extremes. I'm not sure I fully believe that you will find violations of quantum mechanics that show an actually different theory. But I have started more seriously considering the idea that you could have a local hidden variables theory that isn't quite super deterministically conspiratorial, but involves a sort of background wave field that I think this is something you said, that your sort of Bohmian mechanics is the effective field theory of.
Yeah.
So it's like saying you can't have hidden variables that are local, but I can have hidden variables of hidden variables that do all the things we're talking about. And yeah, I don't know. I've only seen a couple of things that discuss in this area, but
no, I think it could be a nice topic for another discussion, because I'm working on this topic, and I will have to show some computations, some results of it.
Okay, that's interesting.
If I may, I would be happy to have the next discussion on that topic. Honestly.
I think it's even probably more fascinating than about probability, but they are connected. Yes, I forgot to say something. What I found very nice in the way of thinking about probability in Bohmian mechanics is that Bohmian mechanics shows that the Born rules is somehow not so different from a standard statistical mechanic. So somehow it's connecting the Born rules to thermodynamics. And this is what I like in the point of view of Bohm and of Bohm and de Broglie and all these people working on statistics for justifying Born rules, is that they say, okay, this is looking like the second law of entropy, which is one of the fundamental law of nature, which is forbidding some evolution and allowing other one. This law of entropy is, which is increasing with time, is one experimental fact, like the Heisenberg principle, like the celerity of light is a constant, is the maximum velocity for transmitting information, and all these rules are somehow effective rules in Bohmian mechanics. They are possible only because you have Born rules. So you have a statistical ensemble which is allowing you to have the Heisenberg principle at the macro scale, to have the preservation of, you have the non-signaling theorem at the macro scale, you have the entropy which is going at the macro scale, and everything is connecting with ensembles and statistics. But at the micro scale level, the dynamic is much more complicated, and the Bohmian mechanic is very promising in that case. Okay, but I agree that it's not probably the only way of thinking about the problem. You have other dynamics. Some people are thinking about stochastic dynamics, other things like that. The Bohmian mechanic has the advantage to be the simplest that I know, and it's at least working in for many wave functions and many Hamiltonian. But I think.
Thank you. So
thanks.
Anyone else? I have a very general point, actually. I wanted to ask you if you know something about that. So I wonder if in the Bohmian community, that's not a nice label, but I mean in the wide community of people working on hidden variables, if there are people that believe that there is actually no problem with the Born rule, and I mean. It seems to me that most of the motivations for liking this theory are actually pretty much like methodological in some sense, also maybe philosophical even. And it seems to me that once you accept the theory, once you accept the reason for having this theory instead of another one, which there are plenty of them, it seems to me that you can accept the theory as a sort of, as a whole, and say, well, we shouldn't be too much worried if we need to have as an axiom that the Born rule works like it does. So I'm just wondering whether some people just say, I usually don't like those people that assume things every time, but it seems to me that I would probably do this if I were one of those people.
I think it's a practical way of thinking about the problem, and in my way of watching the situation is not so much different from what are claiming Joe Goldstein and Zengi with this typicality argumentation. They hide. they hide this with a lot of mathematics, but when they say that you have to use the law of large number, and then you assume already that what is the notion of typicality or probability, you are exactly doing what you are telling. Okay, they assume from the start that the probability function should be what it is. And the reason why they say that is that, okay, it's typical. And when they ask you, oh, do you know that it's typical? Oh, because it is typical to be typical. So there's always an issue.
I was thinking that even more, you know, clear and explicit position. Like, yeah, as an axiom that it's a weird axiom because it relates something to probability. But that's how the theory works, and you need to trust this axiom, which is a weird axiom, and it's part of the thing you buy when you buy the theory. But you know, whenever you buy theory, you're gonna buy something. You know, at least in interpretation of quantum mechanics field, you're gonna buy something weird anyway. So you know, I mean, I'm not saying I was wondering that if there are some people who seriously try to defend the position I just mentioned.
A lot of them. If you want, you can do it like Dur, Gaussian, and Zengi and hide your doubt with a lot of mathematics. Somehow your assumptions are not visible too much, but they are still here. This is somehow what they are doing. But if you are not pleased, you can simply say, okay, be more honest and assume from the start that the probability is according Born rules. And okay, why not? We don't know. The thing is that there's a community of cosmologists which are debating a lot about multiverse and different possibilities from the quantum state of the universe, and they're also using probability distributions. And this is the same. How can we be sure that we can speak about probability for large system like that? You can assume different things. Okay, you can assume different things about probability. Maybe is the best, is the simplest. But what I would like to do personally is to say maybe if you are trying to find some deviation to Born rules to see if it is stable or not. And this is somehow what I did. I tried to show in recent paper that using entanglement or decoherence and things like that it's going to be natural to have Born rules. But again, at the end, I think you're right. You could simply accept it as the law of nature, and say maybe nature choose this as an initial conditions. We don't know why, and that's it. But yeah.
Just to follow on from that a little bit. Yeah, I mean, speaking for foundational physics, maybe it's not as acceptable, but I feel like your point, and also some of the points made in the presentation felt like defenses of things that, I mean, physics happens all the time in every other area. You know, it was almost asking for mathematical degrees of clarity in a physical situation, which when you consider something like general relativity, I mean, Einstein's field equations there, it's just a postulate. And if you look at it, okay, what he's done is he's taken the tensor structure that he needed. He's gone, well, the trivial one won't work. What's the second one that isn't trivial? And he's just run with that. And I believe in general relativity, people occasionally explore what the other ones might look like, but not so much use. So, I mean, it's not like this approach isn't taken all over the place. Mm-hmm. And I suppose, again, if things turn out to be, this is just an effective field theory, it's even more reasonable because it's exactly what they've done in gravity. And they anticipate that, you know, with some sort of quantum gravity, things will clarify. But the idea here being that, okay, well, if you imagine this is some sort of effective field on top, and you have some sort of even more clarifying presence beneath, why not assume that the Born rule is just like this? I don't think getting mathematical justification at this precise level when you're not even sure if it can go further, it's going to end up circular, just like if you were to try and do this with the Einstein field equations.
Yeah, yes, this is the point here.
Are there any other questions? I think if we can, if you like, Aurelien, we could try and go a bit further since we have time.
Yes. Yes, if you want to go, but then, okay, so.
I mean, if as far as you.
Yeah, I'm wondering if people are not already sleepy.
No, maybe just if I don't want you to start something that requires more time to do.
No, in fact, I prepared initially my talk for being in continuity, but I was thinking about the health of people which are listening. So maybe.
But it might be that people need some time to digest and think about. So that
after that, the examples that I want to give are quite simple, and my next talk will be quite short, but it could be a complement of it. Okay, if you want, I can show you. If people is not agreeing, I can go. I can see somebody.
What was that?
well done. No, I think it's better than to do it next time because.
Maybe then some general question about summarizing the elements you provided, because because I was a little bit lost in the explanation at the beginning. So yeah, can you help me to complement the thing? So you started, when you started, you talked about this phase space volume, let's say, and you said that this volume, so given the equation of motion you have in Bohm theory, it is conserved in time. And so then you said, at this moment, so then you said, all right, I will, can you a little bit summarize in few words the line of reasoning you had at the beginning?
The line of reasoning at the beginning was to connect the language of fluid motion that you use in a Schrödinger equation to the probability fluid in a statistical mechanic. Mm-hmm. Because what is not so often understood is that the probability as a double phase, as I say, is on one side is associated with a frequency. So this expression is the best here. Yeah, this is a good one because okay, on one side you have this quantity, which is a distribution of Dirac peak, which is associated with empirical distribution of particle. And we want to identify this fluid of particle, which is the reality, the actual universe, with a fluid which is continuous, which is the chi-square function. And this can only be done rigorously in the limit of n equal infinity. This is the way how people are deriving it in the law of large number.
And I also have a question that I had at that moment. I didn't ask. What I didn't understand on that slide was that from the Bohmian equation, so the equation of motion you have, without saying what is the observable you will find, you have on one hand the evolution of psi, on the other hand the evolution of the position. So this equality should be derived from the equation of motion. How can you impose it? This I didn't get.
You cannot derive it from the equation of motion. Simply, you have to assume already that you have a probability space. This is the thing that people not realize when they are thinking about probability. Probability is a complicated notion because you see the law of large number is assuming. Okay, if you want to say it like that, you have to go back to the basis of probability. If you go, for example, to the work of people like Kologorov, Kinchin, and this kind of people, the Russian mathematicians, they were clearly telling you that you have to define probability having the probability of being additive and in properties like that, like you know. And this probability that you introduce mathematically, you want intuitively to assign the probability to individual events. So, for example, you are doing an experiment like the Stern-Gerlach experiment, and you want to assign the probability number to the individual event. But we have what people are, the Russian mathematicians were very clever because they say, hey, be careful, you are Bayesian guy, you cannot say that the probability is assigned to individual event. It's actually assigned to a collective, necessarily. It means that if you want to apply the law of probability to a single event, you have problems. For example, what is the probability that the King of England will be the Prince Charles tomorrow? This is difficult to define because you need something which is reproducible, so you need a Gibbs ensemble. with atoms, molecules, it's possible to think about that, but with some event like that is difficult. So the idea is to introduce a fluid which is fictitious in the sense it is continuous, it's obeying some conservation law, and then to identify it with the density of particle fluid. So
my question, I think, is a little bit different because maybe it's related to what you assume or not when you write this slide. Because for me, at this moment, you had the equation of motion of psi and the particle. So did you, at this moment, before this equation being written, do you already assume the equation of motion of Bohm or not? That's the thing.
Actually, you could do it more. Yes, because you see, it depends. Yes, in a sense, because yeah, the xi coordinate are the coordinate of the particle computed with Bohmian mechanics. But the general reasoning, the general way of doing that is independent of Bohmian mechanics. You don't need to know the dynamic of Bohmian path for doing that. This is very general way. If you think about it in the standard quantum mechanics, you have the same law. It means that the law of large number is telling you that the probability is approaching the chi-square function, but it's not who exactly, because you have only a finite sample in your universe. For example, if you have n particles, the probability chi-square will be equal to the density, the empirical density, with an error which is proportional to one over the square root of n, typically.
Okay.
So this is it's a very general picture, okay? It's very
but my point is that this equation, for me, if you have the equation of motion for psi and for then you have also the other law that relates to the position of the particle. You take n going to infinity and you can prove this equation. That's the thing I'm confused.
No, you cannot really prove them. You can prove that this quantity is preserved with time. You can prove that this quantity is preserved with time. This is I mean, in a certain sense, these two quantities obey individually to a law of conservation, which is the law of conservation that written here somehow. You can imagine this row space will be this function that the sum of Dirac peak, and this chi-square function is obtained from the Schrödinger equation. And you can derive. You can define the row function with this sum of Dirac peak, and you will demonstrate rigorously, and this is satisfying this equation. This is no problem because you can make a different.
Okay. Yeah. Okay. Because that's about the velocity that we have. We can deduce the velocity, but not the position. And in your thing, that's an equation that relates the position of the particle to the modulus square. So that's why we cannot derive it from here.
Yes, and at the end, if you want to really identify them, you need to go to the law of large number. You have no choice. You have no choice. Or as it was said by Christian initially, you can identify if you want as a postulate chi-square and rho, but then is again as a postulate.
Yeah. Okay. No, I see. Okay. Okay.
Yeah, it's technical, complicated.
Is there anyone else who wants to ask something? Otherwise, I think we can. Okay. Okay, so I think we can just reconvene next week. Everyone seems kind of tired. I definitely am. So
it's better for the discussion, and like that we focus on some problems, and we can. I will make a very short reminder of the issue next time, and then we can show you some other of the way of thinking about the problem.
I would also keep in mind the possibility of discussing what Richard suggested, unless it's already related. But yeah, I mean, I trust you in organizing the talk, your talk. Okay, may I ask you, Aurelien, to make me host again?
Oh yeah. So
you should go on chat and then go on my name.
Yes. Converser, participer.
I wanted to show something to everyone. So don't leave. Give me 1 second. So if you go to the participant and you go to my name.
Yes, participant and Christian Mariani.
Yeah, if you click on other or autre, you should have make host.
it's French.
Sorry about that.
It's always a technical point that I have no idea how to do it. Last time we did it very nicely, but we managed.
If you go to on the participants, you have the list of names.
Yes, yes.
And if you go over my names.
Yes. Plus, yeah, there's no possibility. Nommé animateur. Yes.
Exactly.
You are animateur. Excuse me.
Thank you. No, it's all right. Okay, so just very quickly, since we have those 10 minutes, we are uploading the videos. So this will also go on the website. I'm going to share the screen to show you that it's not my fault if the website is complicated. I guess you already know that.
I did it before. Oh, nobody listening this.
Go to, okay, so the idea is the following. You go to the Quantum Engineering Grenoble, then you go to Fostering the Ecosystem, and then there is a Physics Philosophy interface, which is what we represent. And then, and then we go on other actions, which is actually events and seminar. We renamed it. And once you, I'm sorry, I'm not really not joking. I didn't want to make fun. I'm just, and then the second on the list is the reading group. Now we are trying our best to make this simpler. If someone is willing and also like a good tech person can help me open a website for the group, not just the reading group, but it would be nice to have a small Weebly website where we can put our stuff. Anyway, this is the page, and we have all the the talks we did, the meetings we did. This is my face, as you can see, and this is the last meeting from June. No, not the last one, one of the last ones. And we are going to put links for each of the meetings we recorded, which are almost all of them. And we'll do the same for today's. There is a YouTube page of the Quench. I don't know what the pronunciation is. And so you can also find the videos there. So that's all. Just thank you again to Aurelien, and I'll send you a reminder on Monday-ish. And have a nice weekend. It was nice to see you again, Noel.
Yeah, it was a pleasure.
Thanks for organizing me, and thanks, Aurelien.
Thanks.
See you soon, guys. Ciao.
Bye. Thanks.
Bye.
You. Bye.